Dude, how do fridges work?
Dude, if you think about it, they're kind of like a cycle.
Like a cycle?
Yeah, dude. Like, let me show you.
Dude, did you just have that lying around?
Dude, I don't want to talk about it. So anyway,
This process is a vapor compression refrigeration cycle. Basically, refrigeration is defined as lowering the temperature of an enclosed space by removing heat from that space and transferring it elsewhere. The four components in a vapor compression cycle are the evaporator, the compressor, the condenser, and the throttle valve. In the evaporator, the heat is transferred to the refrigerant, causing the refrigerant to boil into a vapor. The refrigerant now enters the compressor, which increases its pressure. The high-pressure vapor refrigerant enters the condenser, where heat is transferred to the surroundings, causing the refrigerant to condense into a liquid. The compressed liquid finally enters a throttling valve, where the pressure and temperature drop significantly and gets sent back into the evaporator.
But dude, how'd you know the behavior of the gas?
I don't know. I just assumed it was ideal.
You know what happens when you assume?
What?
I don't know, I was asking you.
Dude, maybe you can't assume that it's ideal.
Dude, check this out. Equations of state are used to describe the behavior of gases. The equations describe the relationship between pressure, molar volume, and temperature, with R being the universal gas constant. For example, this is the ideal gas law, which never works because gases never behave ideally. To counter this, there are other equations of state that provide corrections for non-ideality. An example of an equation of state that models real gases is the Peng-Robinson equation, shown here. As you can see, this equation is very different from the ideal gas equation. The Peng-Robinson equation uses A and B to correct for the non-ideal behavior of the molecule in question. A and B are variables that are unique to each molecule. As you can see, depending on their values, they can potentially have a huge impact on the equation. Although the Peng-Robinson equation does a great job at modeling some real gases, it does a poor job modeling others. Each equation of state is made specifically for certain types of molecules. The Peng-Robinson equation was made specifically to model non-polar molecules. Fortunately, I have a handy-dandy chart that lets me decide the best equations of state based on properties of the gas in question. The first leg of the chart is to determine if the molecule is polar or nonpolar. Polarity can have a huge effect on how molecules interact with each other. As you can see here, tetrafluoroethane is a polar molecule, being electron dense on the left side. The next step is to determine if the molecule is an electrolyte or not. Tetrafluoroethane will not ionize in water and therefore is not an electrolyte. Next, we must decide if the gas is under high or low pressure. This is important because higher pressures usually mean that molecules interact with each other more often. For our cycle, we will assume that we are operating under low pressures. Last but not least is to determine how many components our system has. The only component being used in this cycle is tetrafluoroethane, leaving us with the UNIFAC equation of state. Based on our reasonable assumptions and the guidelines of this chart, the UNIFAC equation of state should do a great job of modeling the behavior of tetrafluoroethane.
Dude, so now we have everything we need to solve this!
Dude, but wait, how do we know if it's the same kind of cycle?
Well, let's just check. Dude, that's a countercurrent heat exchanger.
What? Dude, I have no idea how to solve this.
I can show you guys how to do it. In order to solve the countercurrent heat exchanger refrigeration cycle by hand, there are several key assumptions we must make. First, we assume that the evaporator and the condenser each operate at constant pressure. Because of this, if we know the pressure of the exiting streams, we also know the pressure of the entering streams, and vice versa. We can find this pressure with the knowledge of the temperatures at which they operate, using the pressure enthalpy diagram. There is a saturated vapor exiting the evaporator. Using the pressure enthalpy diagram for tetrafluoroethane, we can see that the saturation pressure at 20 degrees Fahrenheit is about 37 psi. Because we also know that a saturated liquid is exiting the condenser, we can also see that this saturation pressure is about 100 psi. Once we know two intensive variables, such as temperature and pressure, our pressure or enthalpy, all of the other variables can be found using the pressure enthalpy diagram. We now know the temperature, pressure, and enthalpy of the streams exiting the condenser and the evaporator. Because we say that all heat exchangers operate at constant pressure, we also know the pressure of the two streams exiting the countercurrent heat exchanger because we know the pressure of the entering streams. We are making the assumption that the streams of the heat exchanger change temperature until they have a difference of 10 degrees Fahrenheit. So we also know that the temperatures of the exiting streams are 10 degrees different from each other, which are 45 degrees Fahrenheit and 55 degrees. We can now define all of the intensive variables of these streams as well. The next assumption we make is that the change in enthalpy across the throttling valve is 0. This allows us to find the temperature of the stream entering the evaporator, which happens to be the same temperature at which the evaporator operates. We then solve for the change in enthalpy and divide it by the efficiency of the compressor to find the work done. We add this work to the enthalpy of the entering stream to find the enthalpy of the exiting stream. Now all that is left is to solve for the power required by the compressor. To find this, we must first find the flow rate of fluid through the system. We know that the evaporator requires 2,000 BTUs per second of heat, so we can find the flow rate by dividing this by the change in enthalpy across the evaporator. This gives us a flow rate of 26 pounds per second. Multiplying the flow rate by the change in enthalpy across the compressor gives us the power requirement of the compressor. So now that I've finished calculating the work required by the compressor by hand, I guess we should plug it into Aspen and see what that tells us. Well, that took forever. So we've made our flow sheets here, this one being the cycle without the countercurrent heat exchanger and this one being the cycle with the countercurrent heat exchanger. And now we can run it and see the values that it gives us. So after plugging everything in and running it with UNIFAC as the equation of state, it gives us these results, with this one being without the heat exchanger and this one being with the heat exchanger. And here we have 354 kilowatts, which is about 335 BTUs per second. This one is 323 kilowatts, or 306 BTUs per second. And that's what we expected. The one with the heat exchanger requires less power than the one without the heat exchanger.
So the difference between our calculated amount and the power that Aspen gave us is most likely due to variations in error on how we read the pressure enthalpy diagram. When we tested multiple equations of state, we found that RefProp was similar as UNIFAC, but other equations did not give consistent power requirements, which supports that UNIFAC was the best model.
Yeah. So that's how you do it.
Dude, that was rad.
Using the pressure enthalpy diagram. Alright, so first I'm just going to solve it by hand using this thermodynamic table here. And I don't know what to say.
Cut.
So anyway, I have this handy dandy chart right here.
So now that I calculated the work for the compressor, I guess we should do it on the computer now and see what Aspen tells us.
Josh, your video.
Incredibly hard amount.